Well, hello and welcome to another episode of Undercooled. Today I'm with Tim as usual and our guest Kevin Jones from University of Florida. And Kevin's a great guy. I've worked with Kevin for years, and it's because of Kevin and because of what we're going to talk about today that I started this whole course with our archaeology department at Michigan called Making Things: 3 Million Years of Materials and Culture. But it's really just a ripoff of what Kevin developed called Impact of Materials on Society. So, Kevin, why don't you tell us a little bit about yourself, your background, how you got into material science, what you do for research, and how you ended up doing Impact of Materials on Society?
Okay, well, that's a lot. Let's see. So my background is, I didn't know anything about material science when I was started college. I was in a summer science program in high school, and I asked for muscle physiology and neurology, and they stuck me in a material science lab and said, go up, figure out how much uranium is in phosphate. And I went, okay. And so kind of fell in love with it. And then I was looking for a job as an undergraduate, and they had a lot of openings in material science. So I went over there and started working in the labs, doing everything from open heart surgery solutions to bioglass. And eventually I just sort of fell in love with material science. I got my bachelor's at University of Florida. And then after that, I did what about half of the material scientists do, which is I went into industry and worked for DuPont for a couple of years making plastics. Basically played on the world's largest Play-Doh fun factory and squirting out plastics for a couple of years. And then went back to grad school and went out to Berkeley ostensibly to play Frisbee, but at the same time decided I would go ahead and get a PhD while I was out there. And I got my PhD in material science there. And then after I got out, I had to get a real job. And it was, Florida or Ohio State, and I don't really like Ohio State, so I went to Florida. So anyway, Ohio State is great, but I like the weather down here. So that's kind of my background, and I've been teaching material science ever since then. So I've been doing that for 35 years now. And in terms of what my research area is, I've actually kind of transitioned from the plastics and polymer field, which I did as an undergrad, into semiconductors, and I do more semiconductor materials as my graduate work, and then on through as a professor. So I've been working on electronic materials for the last 35 years, primarily with silicon industry and helping them figure out how to make chips smaller and faster, so that we can actually do conference calls like this. Let's see. In terms of the IMOS class, so I was chair for a while, and I noticed when I was chair that we had, a lot of kids were having trouble making a connection between why they were taking these gen ed courses and what engineering was all about. And I said, this seems like we should try to figure out a way to introduce the kids to what engineers actually do as freshmen, so that they know what we do, and even if they're not going to go into engineering. And so I called up a friend, S1E8, who's a professor in humanities, and I said, I'm interested in doing a class, and you teach a course on the humanities related to technology. And I said, you want to do a class together? And she said, yeah, sure. So we picked up Steve Sass's book, The Substance of Civilization, and said, well, let's start with this. And then she said, I got a whole bunch of friends and humanities who might be interested in this. And so I said, great. And so we sat down and had a workshop. And basically I said, pick a topic and I'll find a way that materials impact that topic. And so I had people come up with, I'm really interested in Andrew Carnegie. Well, that's easy, that's steel. But then I had others who were like, I'm really interested in Romans, and I study the Colosseum. I said, great, that's concrete. And so we kind of went through it one at a time, and we found one. It got a little weird at some point. I had a person do French poetry, and I was like, that's tough, but in the end, I kind of went, well, diamonds, and they were like, yeah, that was really big in the Louis XIV, So anyway, so we did diamonds as part of that one. But that module eventually got phased out, and we did other things. But so it's been a lot of fun to just create new modules, or, basically looking at how materials in society have co-evolved, right? And so that was the genesis of the course.
That's awesome. And so I think you also told me at one point that you were trying to increase enrollment in your department. Was that one of your initial goals?
That's exactly right. Initially, I was thinking, when you come to the university, you don't know what material science is about. You know what a mechanical engineer does, you know what an electrical engineer does, but what's a materials engineer? I don't have any idea what that is. And the one nice thing about materials engineering that makes it particularly useful at the freshman level is that it's very tactile. You can touch a material and you know what it is. And so, and you spent your life around it. You may not be aware of it as much, but you spent your life touching and interacting with materials. And so it meant that I didn't have to dig into a lot of math and lose a whole bunch of freshmen to differential equations or something like that. If I just want to simply talk about what's soft versus hard, or what's conductive versus non-conductive. And so it allowed me to gain access to a whole group of engineers that were coming into the university, said they wanted to do engineering but didn't know about material science. And so I could teach them about this. And of course, what happened, which was really interesting, is I got a lot of the non-engineers really interested in it. And they became very excited about learning more about what engineers do and how this works and whether or not they have a role in this process. So yeah, it's been useful in terms of creating more, exposing more kids to material science, and eventually that actually resulted in a significant increase in our undergraduate enrollment, which was a real nice benefit.
That's awesome. And so what year did this actually start happening?
We kind of started the class around 2010. And so it's been evolving, and we've been adding new modules and stuff like that since then. And it's just last year at University of Florida finally got Gen Ed credit. So it's now a general education course, which is great because it means we get a lot of kids signing up for it real fast. The downside of it is I'm not seeing as many engineers because the other disciplines jump in there real fast and register for it. So this class was interesting. I usually have about 90% engineers, and this time I had 90% non-engineers out of my 130 students. But they did fine in the class, and they're very creative individuals, and so I think it was great fun from that standpoint.
Oh, that's great. And you also, along the way, got involved with the Materials Research Society and the National Science Foundation with this course. What did you actually do with them?
Well, one of the things we wanted to do with this class when we came up with it was to develop a way to disseminate it, because it became obvious that we had a very large DoD grant to begin with, actually out of the Office of Corrosion. And that helped us make a lot of the movies that we use in the course, the videos. And but part of that was also that we said we would try to disseminate this around because we wanted, the Office of Corrosion wanted to increase the number of materials engineers out there. So they were very interested in finding a way to attract more students into materials engineering. And they thought this course might serve that purpose. So we wanted to disseminate it, and that meant that basically we worked very closely with MRS and with the NSF to create new modules that were more, even more updated and more appropriate for certain things like photovoltaics or membranes for water purification, et cetera. But also to create all the content into a single package so that we could get it out to other universities around the United States. And so we've been working on that with NSF and with the MRS over the last decade or so.
And so how many other programs have adopted a course like this?
Well, I tell you, it's hard to keep track of it. I think we're up to maybe 10 universities that are now teaching it around the country. We've disseminated it to a lot of universities. And the nice thing about it is it's all packaged up. We give them all the modules, we give them all the homeworks, we give them all the notes, we give them the videos of the lectures, we give them the demonstrations, videos, the whole 9 yards. So the barrier to introducing the class should be very low. And because it's all free and open sourced, and I even give them the Canvas shell and say, here's the shell, which we spent years developing. And so it makes it very easy to start the class. And so I think a lot of people who are interested in trying to start a new course, for example, University of Central Florida wanted to do this because they were starting a new materials program. And I just heard after 2 years, they've gotten it accredited and they got 140 students already in materials there. And so it's really helped them kind of set their base and get the program off the ground. And so, that's been really, really helpful in terms of having the MRS, supporting this and helping us disseminate it.
And obviously, we're one of those programs that have done the same thing, and your material was fantastic to help us. It might be interesting sometime to have like a Zoom meeting of all the programs who are doing it, so we can actually talk to each other and see how we might.
I mean, one of the things we wanted to do was make it so modular, such that if another university developed a new module, we just insert it in with the rest of them so that we could disseminate it around, because we already have more modules than you can teach in one semester. And, it's nice to be able to kind of pick and choose to tailor the program to whatever your university, and your personal interests are, right? And I mean, one of the challenges with this class is finding someone on the other side of the fence over in liberal arts that is interested in co-teaching it with you if you want to go that route. And some people do, some people don't, but it helps if you do. And if you do, then they have their own interests. And so you can say, well, here's, 15 modules, pick 10 that you think we would want to teach together. And it makes, you can customize the course to whatever you want to do.
Right. And that's what we did. I found people in archaeology who were really interested in this. And they're also really interested in all of our equipment in our undergraduate lab because they would like to use it. And we've started some projects, and we even now have a module where we bring everybody over and everybody gets to put on the high temperature gear and cast aluminum, just like they did in the Bronze Age with a sand mold. We pushed in a little block M and they do some casting, and they love it. So,
sure.
But one thing I noticed, I just went and did a Google search on impact of materials on society, and I don't see any of the information up anymore. The only thing I can find is the textbook. I know you have an open source textbook, which is fantastic, and we use that. But where are all the modules now?
Yeah, that's a good point. I mean, when MRS decided that they were going to back away from dissemination, they kind of took down that stuff. And so right now it's more on people contacting me, and then I send them everything. And so it would be nice in the future to work with another organization that would be willing to put it up on their website and host it, so that we could have a nice clear path to dissemination.
So Tim and I are both on the TMS Education Committee now. Would you
That'd be
be
great.
open to TMS adopting it and putting it up on their website?
TMS, ASM, whoever. I mean, if TMS wants to do it, I'd be happy to work with TMS on it.
Yeah, or ASM. I don't think it matters, but I think it's important that this material is up there, because I think it's a fantastic course. And I still, to this day, one of the major problems affecting all materials programs across the country, except maybe Illinois, is getting new majors. Illinois does it. I don't know how they do it, but they do it. But the rest of us, it's really hard to fight computer science with the kind of salaries that they're making. And then, we're a small department. Like you said, nobody's heard of us. So actually at our, we're going to run the NAMES conference, the North American Materials Education Symposium, is going to be in Ann Arbor next summer. Hopefully
great.
you can come up for that.
Yeah.
And we're going to have a session focused on beyond the teachers' camps. How do we attract students to material science? The teachers' camps are fantastic. They've been doing that for, 50 years now. And they need to keep doing that. That's great. But that's the only thing that's really out there. And I think this IMOS is a really valuable approach to helping with the problem.
It's very accessible, and it gets kids very excited about about materials. And so that's the fun part.
So, so until it's up there, people should just contact you, and you'll help them out. Okay, so we'll make sure that your email is in the show notes, and any maybe a link to the open source textbook we'll put in there, and we'll be asking you to give us a hand with some of those links.
I mean, we've been disseminating. I know in Bolivia they're developing a Spanish version of IMOS. So we'll have that as a second language source. And then also we've been working a lot in disseminating it in Africa, because actually UNESCO the United Nations wants to have this as a required course in all of the nanotechnology programs in Africa. So we've been working a lot with the African universities to start teaching, we've offered a couple of workshops over there to help teach them how to teach the class. So it's getting around, but it would be really good. You're absolutely right. I mean, it could be a very good recruitment tool for material science programs.
Okay, so Tim, do you want to ask any questions about the pedagogical approaches that Kevin is using in this class?
Yeah, I do. The first thing I was wondering about is with the modular structure of the course, is this something that a single module could be imported into an existing class? For example, I've got a freshman course where I have a week and I'm not really sure what to do with this week. Would it be possible to bring in one module that I think would be particularly interesting, and how would I implement that with my students?
Yeah, absolutely. I mean, I think the course it's not required to see a particular module in order to do the next one. So you can teach them independently. There is some continuity in certain situations where we've talked about something in the past, and we might reference it. But by and large, it's not going to be a problem with teaching an individual module. The modules are set up such that there's a science-based lecture that you open with that kind of gives them the historical and the scientific background that they need to understand what the material is. And usually right before I do that, I actually hand them samples. So if we're like doing copper and bronze, then I will hand them out samples of copper and bronze wire and say, just tell me what you see. You got it in your hand, bend it, flex it. Is one stronger, one stiffer than the other one? What's the color? What's do you think it's conductive, not conductive? Just give me the general properties. And then we talk about what it is and the concept of an alloy, for example, if it's copper and bronze, and how alloys are formed. And then we talk about the historical context of when was it first discovered and all that sort of stuff. And so, but then the second lecture is typically a social science lecture. So it's more about how did this, it might be a particular case. So, for example, if we're talking about iron and steel, it might be the story of Andrew Carnegie. Or if we're talking about aluminum, it might be the story of Alcoa. And so they learn something historical about that material and how it impacted a certain period of time. And then they watch a video on the next day when we're not in class, where they actually see a video of a future material. So, for example, if we're talking about steel and we're talking about materials that might change, or evolve, or then it might be magnesium alloys, which are replacing steel in certain applications. So they learn a little bit about a new material. And then on the next time we meet, we flip the classroom and form groups of 4 or 5 students. And then they have to work on a problem like designing a new product built out of magnesium, but using, the principle that we taught them in the social science lecture. So the idea is that at the end of the year, they've learned about 11 classes of materials, but they've also learned sort of 11 social principles along the way, like entanglement or like creative destruction. And these principles are something that they can then apply to any future problem that they have, right, in engineering or whatever. So it just kind of broadens their perspective on the fact that when you innovate and you create something, you're not doing it in a vacuum, you're doing it with society. And so they learn to think about more globally about, gee, is this a conflict material? Gee, is there child labor involved in creating this product? Gee, how do I address sustainability with this problem? How do I deal with, a cradle to cradle kind of concept rather than cradle to grave concept in creating a new material? And so we try to get them to think more socially about this. And I think they enjoy that very much. So yeah, you can certainly teach a module as a standalone feature. You would just have fun with the class on that one day where they flip the classroom. They'd be in new groups, right? But you could do it.
That sounds really interesting with the in-class discussions. And now you've got me wondering, as you have this mix of engineers and also non-engineers in the course, when they're having these, team activities together and you have this mix of people who are and are not engineers, what's that like? What comes out of that you might not get in a normal engineering class?
That's the absolute best thing that happens, right? Is that you get this cross-fertilization, right? I like to tell the non-engineers that they need to understand that they have a seat at the table, right? That when we're innovating, a lot of times they're bringing a very different perspective on what we think is important. And if they bring that perspective, then this is something that engineers might not think about. And it could be the difference between having a successful product and having a not successful product, because they've thought about, gee, how is the customer really going to use this? What is important to them? What do they think is going to be, that has nothing to do with the engineering of the product itself, but just the perception. And so when you're dealing with groups of non-engineers and engineers and they're all kicking it around, it's a lot of fun to watch that interaction go off, because they just bring very different perspectives on how they can solve this problem. And a lot of the problems are very open-ended questions of just, design something that does this. How are you going to create a marketing campaign for this, right? Things like that. And they have to kind of work in groups. And so they have to bring their perspectives and say, well, that slogan that the engineer came up with for the marketing campaign is horrible because it's 37 words long, and it's not, and just do it works really well as a slogan,
Uh-huh.
And we're going off on some technical rampage about what, why this product is really important, rather than just doing it. So, I think it's a lot of fun to have that interaction. I really value the fact that I've got non-engineers and engineers commingled in the class.
Do you use any software to build your teams to take advantage of that diversity in your class?
We haven't. It's a good question. And one of the things that I've been trying to figure out is, and we use a little bit of software. We use the Granta software package sometimes. Although we found that with that package, it was a little challenging for one module to teach them all Granta. And so it's easier just to hand them the sheets and say, look it up, and print it out, rather than to deal with the interfaces and the challenges of downloading a program. So I tried, but we encourage them actively to use the web all the time on these problems, because we'll say, all right, you can build, for example, we do this whole thing with gold nanoparticles, where we say, you're developing a new drug using gold nanoparticles. Do you think this will impact the price of gold? And of course they say, yes, it's a new application. And then we sit down and figure out that you need 2 kilograms of gold to create all the nanoparticles necessary to treat all the pancreatic cancer in the world, right? So it absolutely has no effect on the price of gold. But then I say, well, if you could do it with titanium rather than gold, right? And it was exactly the same efficacy, right? Which one would you use, right? And they look it up and they come back with, well, we use titanium because it's cheaper. And then I say, or tantalum, and then I say, okay, great. Well, is that a conflict material? And they go, what's a conflict material? It's like, oh, well, and what about the gold standard? People might, the price is nothing, right? But people have a perception that gold is better than tantalum or whatever. So, so just understanding that from an engineering perspective, you can look at it, the economics, or you can also look at it from a humanistic standpoint, and you get a very different answer. So just making them aware of that.
So I was actually referring to how you make your teams. So like I've been using CATME, CATME.org.
Okay.
It allows me to provide a questionnaire to the students. And I ask them, what's your major? And I ask them, what year are you in school? And then I form my teams based on the diversity in the class, including, race and gender, of course. But I get teams with engineers next to business students, even kinesiology students, and English majors.
There you go.
And having each team be very diverse with their outlooks, I find leads to incredible creativity in the way they approach these marketing plans for these projects that we're using, because we're using all the ones that you developed.
Oh,
and
that's
a
great.
lot of fun.
I have not used that program, but that sounds awesome. I would definitely look at that next time when we teach the class next fall, because it sounds like a great way to form up the teams.
It is. And then it also gives you the opportunity to have the team members rate each other. So it has a team maker capability. And then it has a peer review capability. So if somebody never contributes, you don't have to give them the same score. So
right. Well, we do that manually, but it'd be nice to have it be done automatically. I just hand out a sheet and say, evaluate your other teammates, and that becomes part of their grade. But you're right. We have tremendous diversity. I had dance majors in the class, sitting next to electrical engineers. So,
I had a student last year who didn't show up He just stopped coming. And I asked, has anyone seen Luke? And someone raised their hand. He goes, oh, he's my teammate. I go, no, he's not. He's on team 15. You're on 12. He goes, no, you don't understand. He's on the hockey team and I'm on the hockey team. And the reason that he's not here is he got drafted. And so he's playing for the New Jersey Devils now. And that night he scored the overtime goal.
Wow. There you go.
And I had no idea.
Yeah, that's funny. No, that sounds like a great software program. So I'll definitely want to get a copy of that from you.
All right, I'll put that in there. You have to pay for it now. It's $2 a student. But it's possible that Florida already has a site-wide license for it because it's used in lots and lots of classes.
Cool.
So where do you think, you're making these extra modules here and there. You're trying to broaden it with UNESCO and other places. Do you think there's ever going to be a MOOC that you might want to create for this course?
Thought about that. That's a really good question. The MOOC is an interesting vehicle for disseminating information, and I think that it's something I would definitely consider in the future, especially if there was I've thought about how do you get this out to a more general audience. There's so many people out there that are just really fascinated by the stories behind materials, right? And just so I think a MOOC would be a really interesting way of. I have a lot of parents who tell me they'd love to take the class, right?
Right.
And so that the MOOC might be the best way to let them enjoy some of this thing because the stories are fun to tell, and they find it fascinating. So,
well, you might remember, we haven't been successful at an open source materials textbook.
Right.
But really, my main motivator for that wasn't to compete with Callister's book. That was never the point. The point was, how do you create an open source textbook that you could build a MOOC around? And you're really making the MOOC for parents more than for students. So
Right.
we want it to be very low level so that they can appreciate it. And the more I think about it, you've already done that. You've already got the textbook. It's already at the perfect level. So maybe we should just, start recording some lectures, and maybe it would be a good project for the community that you've already built of all these programs. We can distribute the work, and it really wouldn't be that difficult to do.
It was funny during COVID. I actually taught the class online, and I went into a recording studio, and so I've got recordings of all the lectures, the science lectures, done, already done. So basically, that work is there, right? And so, you're right. I think it would just be a matter of organizing and pulling some stuff together and getting the new ones on there and organizing. But I think it would be a fun MOOC. I think people would enjoy it.
As far as I know, the only materials MOOC out there is what Jim Shackelford has done. But you have to buy his book.
Oh.
And that's a barrier.
Yeah,
and
right.
It's more focused on educating students about intro to materials. Whereas I think the big impact of this would be educating non-materials people about what materials is, especially parents, because you know how important it is to get parents on board to get their kids to want to become a materials major. They're like, what's materials? I never heard of that. You need to be in a really broad field like chemical engineering. And I'm like, are you kidding me? Materials is far broader than chemical engineering.
That's right.
But they just don't know.
You're absolutely right. I think having the parents on board, because typically I would recruit students in the past before it was a gen ed course by going to the preview sessions with the parents and getting the parents convinced that their kid should be taking this class. So these are all freshmen visiting with their parents, and the parents were always saying, oh, I would love to take this class. This sounds really fascinating. So I think this could be a very good recruiting tool, is to have a MOOC for the parents, right? And then see if they don't start to say, hey, have you thought about material science? So it might
so let me ask you a quick question. You keep saying that it's now available for gen ed credit. What does that mean for you? Because in our program, we've been giving, every student gets credit for it, free elective credit, or in the case of engineers, because it's taught with an anthropology number, and archaeology is in our anthropology department, it actually counts for one of our distribution requirements in engineering. for, we call it intellectual breadth. The course counts as a social science.
Right.
It does not count as an engineering course. It's not sciencey or technical enough, but it does count for that. But so what does Gen Ed mean at Florida?
So at the University of Florida, we have these things called, so before it was called a technical elective. And a technical elective was something that the parents had to pay for above and beyond the required courses. So if you had, because we have, the technical electives have sort of gone away because of the certain number of hours and the programs are all prescripted. So, but there's the Gen Ed courses are now under what's called a Quest. We call them Quest 1 and Quest 2. And these are, every student is required to take a certain number of Quest credits. And so, and the Quest can be in social sciences or physical sciences. And so this course got listed as a Quest 2 physical sciences course in anthropology. And so, so it's like yours. It's an anthropology class, but because it's a Quest 2, it meant that it satisfied that physical sciences requirement. And so we normally would if we were trying to have a class of 150 students, it would take me going to preview sessions for the entire summer to get close to 150. And now that it's a Quest 2 class, it filled up in a week and a half, I think, roughly. Yeah. Spring, and I think it'll go even faster this spring. So
I'm jealous. We've tried so hard. At Michigan, there's a natural science requirement for people in literature, science, and the arts. And they refuse to allow any engineering course to count to that because they want student credit hours. It's really selfish on their part. And it's, what a shame. Well, I mean, I've tried so hard.
Sort of way here, it's the same thing. They don't want engineers teaching Gen Ed courses. So that's why we have it actually listed in anthropology. And my chair is nice enough to let me go ahead and teach it. She said I can keep teaching it for as long as I want to because it has such a positive impact on undergraduate enrollment. She doesn't care about giving up the three credit hours of class, student credit hours. So, but you're absolutely right that there's a little bit of a barrier there on the part of the liberal arts. And so we found a workaround, and this workaround works great. So, I think every school is different. I know that at Boise State, they were able to get it as a Gen Ed requirement as well. And so a lot of other schools are doing that. And it just really it mitigates the whole recruitment process. It just makes it trivial. So,
Yeah. As you're talking about this increase in enrollment, which is fantastic, and how quickly the course is sort of selling out, do you have any concerns with the scalability of the class? Like, do you think it can just, could it keep getting bigger? Would there be other aspects or changes to the pedagogy you'd have to bring in to make it grow?
So the Quest 2 courses are limited. Right now, most of the Quest courses are 25 or 30 students. I actually requested it to be the largest possible, which is 135 students. And I've got a classroom that seats 225, so I can take 135 students and mix them up into groups of 5 and still have spaces between them, and parse them out around the room. It can't get any bigger because that's just the limit that we have on our Gen Ed courses. They don't want them to be 500 or 600 type seat persons. And so I'm not worried about it. I think if you were trying to teach it to more students, I would just offer more sections of it rather than try to cram more kids into the classroom. So.
Right.
But yeah, you're right. I mean, it's a challenge when you try to grow it much bigger than that. We've gone as large as 175 students, and it worked fine. But I think you just do run out of room in the room at some point. So
that's great.
And the other thing is that during those flipped classroom sessions, I tend to walk around and talk to each group. One of the things we do is like we have them come up with a design or a solution or a slogan or whatever it is. We have them post those up on the board, and then we vote on it at the end of the session as to who came up with the best idea, right? So everybody loves that competition, so they want to spend a little time making sure that they have a chance to win it all. And I spent a lot of time talking with each student, each of the groups, and so it would be hard if when I got 30 groups, I can get around to it. If it's 60 or 70 groups, it'd probably be impossible. So it's a good point, though.
So with all the attention towards generative AI, I realized there wasn't generative AI back when people were in the Bronze Age or the Stone Age. But, it's revolutionized a lot of material science with materials discovery and with using AI to handle these very large data sets. I wonder if there's room for a module on that where we actually talk about information transfer and how it was done. Because I think one of the things I learned by teaching this course, I never realized how sophisticated ancient communities were with trade routes and all these things. I learned from my archaeology colleague how, it wasn't that steel made better blades. It wasn't true. Bronze blades were really, really good, but it was all the information got lost when they got sacked by people from the north and the east, and all the trade routes, all the trade secrets all disappeared. And
Right.
it took hundreds of years for that to come back. And of course, we learned this with COVID. One little thing with COVID destroyed our supply chains, but we were able to recover really quickly. Whereas back in the golden age of Greece, when that fell apart, it took hundreds and hundreds of years to recover that. And that's when they had hotter fires and they were able to find iron much more easily everywhere. That iron started to become, a dominant technology.
Absolutely.
And so a lot of that probably relates to this new revolution that's starting with AI. So I think that would be a fun module to think about building into it.
I think it would be great. Actually, I think I was thinking about that with the silicon module as a flipped classroom exercise, is to let the students really explore ChatGPT or Chat AI programs and really have an exercise of how does data collection work and what could you use it for, right? So, as you were saying, if you can mine the sources correctly and limit the sources, then it makes it a lot more effective in terms of teaching for students to be able to grab the information they really want to learn about, rather than sifting through a whole bunch of other stuff before they can find that information. And so that accessibility is really tremendous. And so I think it would be really fascinating to have the students kind of play with it and experiment that, with an AI program. And AI is a huge deal at the University of Florida. I mean, we just hired 100 faculty in AI in every department.
Wow.
So they are, this is, NVIDIA made a humongous donation, built a building and the whole 9 yards. And so AI is all over the place at this university. And so it would be good to try to think about how to incorporate that into this class.
It'd be really great to have the students engage with the physicality of all these computational processes as well. How is a data center built? There's
Right.
so much material science in enabling that physical substrate that all this computation is done on. That could be another really interesting aspect to connect to sustainability and so on.
Exactly. And we talk about the carbon footprint of a data center, right? And are you thinking, and this is really important for the students, because then they start to think a little bit more about, okay, what could I do to mitigate that going forward? One of the things I was, impressing upon them is that we've gone from worrying about making chips faster to making them more efficient, right? That's the new driver for the whole semiconductor industry, because we're using so much power to power these clouds, to power these data centers, that it's not about speed anymore. It's not about how fast you can launch Microsoft Word like it was in the 90s. Right now, it's all about how many joules does it take to run this computation. So I think they're starting to appreciate the fact that this cloud is a real thing and it has a real footprint. And you're right; it would be really interesting to impress upon them and have them do a fun analysis of exactly what this is physically looking like from a material standpoint. Because it's so ethereal to them, right? It's just something that happens on their computer, and they don't, and it's not even on their computer. So.
All right. Well, we're already around 42, 43 minutes into this, and I just wanted to thank you very, very much for being willing to come and talk to us on our budding new podcast. And so thank you so much. And I'll send you a copy of this so that you can help us get our show notes really in a good shape. So with that, I think I'll sign you off. So please stay on until everything uploads. And Thank you.
Thank you
Thank
very
you
much.
so much.
You're welcome.